Usually when we talk about the software we use every single day, there's this expectation of absolute transparency. It kind of feels like a glass box.
Right, yeah.
Like you type on a keyboard, a character just magically appears on the screen, and the computer fundamentally understands what you want.
It creates a really comforting illusion, honestly. I mean, we naturally want to believe that the high-level code we write is just a one-to-one reflection of what the machine is actually experiencing at hardware level.
But the moment you step into the world of programming language design or, compiler architecture, that glass box just completely shatters.
Oh, absolutely.
You realize you aren't looking at a transparent machine at all. You're looking at a highly orchestrated magic trick. Everything from how a simple number is stored to how a function remembers a value is built on these layers of elaborate, sometimes really fragile compromises.
And those compromises have a real measurable cost. Every piece of syntactic sugar or developer convenience, it has to be paid for somewhere down the line. Usually that bill comes due in compiler complexity or runtime overhead.
Which brings us to our mission for this custom deep dive. Today, we're basically pulling back the curtain on that magic trick. For you, the listener, we are breaking down the core architecture of variables, bindings, and scope.
Yeah, we're unpacking the Class 18 notes from your CS330 Programming Languages and Compilers course.
Exactly. Because understanding these invisible costs isn't just about, passing a midterm. It's the only way you're going to survive the compiler you're actively building this semester. So let's start with the absolute foundation. The humble variable.
Right, because if we want to understand compilers, we have to look at the physical reality of what they're actually manipulating.
Right.
And to do that, we have to go all the way back to the von Neumann architecture.
Oh, the classic von Neumann bottleneck.
Exactly. The central issue of modern computing is that the processor, which executes the instructions, is physically separated from the memory, which actually holds the data.
Right, they're in two separate places.
Yeah, so a variable is really just a human-readable abstraction designed to bridge that physical gap. It's a stand-in for a specific memory cell.
But that abstraction is incredibly leaky, isn't it? I mean, take something straightforward like an integer. An integer type maps beautifully to the hardware.
Yeah, perfectly.
Uses a native binary representation. You just drop it right into memory, and the CPU knows exactly how to read it. But a floating point number, that doesn't map cleanly to native hardware at all.
Not even close. A floating point number is essentially an entire mathematical equation crammed into a single memory address.
Wow.
Yeah, it's based on scientific notation. So the computer has to separately store the base digits, the mantissa, and the zeros, which is the exponent.
Oh, I see.
So every single time the CPU interacts with a floating point variable, it has to actively reconstruct that number using all these complex mapping operations. It's a massive amount of hidden work.
It's kind of like cooking, right?
Yeah.
An integer is like buying a pre-baked loaf of bread at the store. You just slice it, you eat it.
Sure.
But a floating point number is like buying flour, yeast, and water. Technically, it's bread, but the kitchen, or in this case, the processor, has to do a lot of active processing just to make it usable.
That's a great way to put it. And the language designer has to make a critical decision here. Like, how much of that processing overhead do we actually expose to the programmer?
Right. Do we hide it or show it?
Exactly. Some languages try to make the internal structure obvious right away, like Perl, for instance.
Oh, yeah. Perl has those symbols.
Right. It forces you to use an initial character like a $sign for a scalar or an @ symbol for an array. It essentially bakes the high-level top metadata right into the variable's name itself.
Which gives the compiler an immediate heads up about what kind of memory structure it's dealing with.
Exactly.
But it also makes the code look like a chaotic soup of symbols to a human reader. I mean, it's hard to look at. And speaking of readability, we really have to talk about case sensitivity.
Ah, yes. The classic debate.
Yeah. In many languages, myval with a capital V, myval in all lowercase, and myval in all uppercase, those are treated as entirely separate locations in memory.
They are.
I have to push back on this, though. If case sensitivity constantly frustrates language learners with all these invisible typos, is it actually just a massive design flaw that we've all been forced to accept?
That is a very common frustration, I hear you. But it's not a flaw so much as a historical hardware constraint.
Wait, really? Hardware.
Yeah, early compilers were absolutely starved for memory and processing power. Forcing an exact, case-sensitive binary string match is computationally dirt cheap.
Oh, I get it, because A and A have entirely different binary values.
Precisely. Doing case-insensitive matching requires the compiler to perform extra conversions on every single character before comparing them. The strictness was basically a survival mechanism for early machines.
Wow. So things like camel case, where we capitalize the first letter of each word to make variables readable, that's really just a human band-aid. We invented a stylistic rule to stop ourselves from tripping over the compiler's rigid binary demands.
We adapted to the machine, yeah. And the machine's strictness goes far beyond just the name of the variable. It also heavily polices how you interact with that variable's memory address.
Right.
This is where we get into the difference between a law value and an R value.
Okay, let's unpack this, because this concept definitely trips up a lot of people. The all value is the left-hand value, and the R value is the right-hand value.
Right? Generally, yes, but let's look at the actual mechanics of it. The all value is the physical memory address itself. It's the location where data can be written.
Okay.
The R value is the fetched contents of that address. The reason compilers care so deeply about this distinction is because reading a memory address requires a completely different set of CPU instructions than writing to one.
So if I write x equals y, x is the L value. The compiler is prepping to write to the physical address of x. But y is the R value. The compiler isn't touching y's address to change it. It's just fetching whatever is currently parked inside of y to copy it over.
Exactly. And the compiler has to strictly enforce this rule. You can't put a literal number like 5 on the left side of an assignment statement.
Because 5 is purely an R value.
Right. It's a concept. It's not a memory address. You can't physically write data into the concept of 5.
That makes total sense.
Yep.
So once we understand that variables are these complex physical memory abstractions, we run into a massive timing problem.
We do.
How does the compiler know what a variable's type is or where it lives? And maybe more importantly, when does it figure that out?
That introduces the concept of binding.
Right.
Binding is simply the act of associating an attribute like a type, a value, or a memory location with an entity, like a variable name. And the exact moment that association is locked in is called the binding time.
And binding times are scattered all over the life cycle of a program. You can have bindings happen when the language is designed, when the program is compiled, when it's linked, or literally milliseconds before the code is executed.
Yeah, it's a wide spectrum.
Let's look at the classic example from the notes. A single line of code that just says count equals count plus 5.
If we connect this to the bigger picture, the amount of invisible history in that single line is staggering.
Let's hear it.
Let's assume we're writing in C. The fact that count is an integer is bound at compile time. The fact that the plus symbol means mathematical addition is also bound at compile time.
But if we were writing in Python, the type of count isn't bound at compile time. It's bound at execution time, right as the program is running.
Yes, exactly. And it goes even further back than that. The range of possible values that count can actually hold, that was bound decades ago at language design time.
Right, when they decided what an integer even is.
Right. And the internal binary representation of the literal number 5, that was bound at compiler design time.
It's actually somewhat eerie to think about it that way. You type the number 5, and you're inheriting a rigid architectural decision made by some engineer in the 1970s.
You really are.
I look at binding times like organizing a major event, like a vacation. Doing it months in advance is static binding. You book the hotel, you finalize the flights, it's highly efficient on the day of the trip, and everything is guaranteed to work out, but it's incredibly rigid.
Right. You can't just change your hotel on the morning of the flight.
Exactly, which perfectly describes compile time binding. You do the heavy lifting up front, so the execution is as fast as possible.
Right. But dynamic binding.
Oh, dynamic binding is like refusing to book a hotel until your plane literally lands in the city.
Exactly.
It's incredibly flexible. You can decide where to sleep based on the weather or your mood, but you spend the actual vacation frantically making phone calls and doing administrative work instead of just enjoying the trip.
And that frantic administrative work is the exact hidden cost of type binding, which is easily the most contentious topic in modern programming languages.
Oh, let's dive into that. We have static type binding, where the type is locked in before the program even runs. You either explicitly declare it, like typing index, or the compiler implicitly figures it out based on the context.
Either way, once it's set, it's set.
Right. But dynamic type binding completely flips the script on that.
It does. In a dynamically typed language, the variable itself isn't bound to a type at all.
Really?
Yeah, the variable is essentially just a blank label. It's the value sitting in memory that carries the actual type information.
So X could hold an integer on line 10, then you just reassign it to a string on line 20, and the program doesn't crash.
Yeah.
Label X just points somewhere else.
Exactly.
I have to ask, though, isn't this just the language designer being, well, kind of lazy on behalf of the programmer? Like, we don't want to bother typing out our data types, so we force the computer's runtime to work overtime and do thousands of extra checks a second to figure out what the data is.
I mean, it's definitely a prioritization of developer speed, but I wouldn't call it laziness.
Fair enough.
It enables incredibly powerful generic programming. If a function doesn't care about types, you can pass it anything and it just works. But you're absolutely right about the performance tax.
Yeah, the overhead.
Dynamic typing strips the compiler of its ability to catch errors early, so all of that type checking overhead is pushed directly onto the runtime environment.
So the computer has to constantly pause and ask, wait, what type is this value right now? Is it actually safe to add these two things together?
Exactly. Every single operation requires the runtime to inspect the descriptor block attached to the value before it can safely execute the instruction. That constant querying is a massive drain on CPU cycles.
Okay, here's where it gets really interesting. We've established what a variable is and when its type is bound, but where is the actual data physically sitting in the computer's memory?
Right.
And how long is it allowed to stay there before the computer reclaims the space?
That is the domain of storage bindings. And we generally categorize memory into 4 distinct neighborhoods. The most rigid neighborhood is static memory.
Right. With static variables, the memory cells are bound before execution begins, and they stay locked in place until the program completely finishes.
Forever.
It's great for global history, keeping track of things globally, but it has a fatal flaw, right? You cannot use static memory for recursive functions.
Because the physical memory address is completely fixed. If a function calls itself, the second instance of the function would overwrite the exact same static memory cells used by the first instance.
So the original state is just destroyed.
Exactly. So to solve the recursion problem, engineers created stack dynamic variables.
Ah, the stack.
Yes, and this introduces a mechanical process called elaboration.
Elaboration, okay.
When the program runs and reaches a variable declaration, the system physically moves the stack pointer down to carve out a fresh block of memory on the runtime stack. When the function finishes, the pointer moves back up and the memory is instantly reclaimed.
It's incredibly orderly, kind of like a stack of plates in a cafeteria.
Oh, that's a good analogy.
Yeah, you pull a plate off the top, you put a new one on top, because every function call carves out its own fresh plate on the stack. Recursion works perfectly. You never overwrite the old plate.
Right.
But the downside is that constantly carving out that space takes runtime overhead.
It does. But the bigger limitation of the stack is that it's strictly last in, first out.
Oh, right.
What if you need a complex data structure, like a massive linked list or a tree, that grows and shrinks unpredictably over the life of the program? The stack just cannot handle that.
Which takes us out of the cafeteria and into the explicit heap dynamic binding.
Yes. I think of the heap as a massive, completely empty warehouse. There are no rules here. You, the programmer, use explicit runtime instructions to allocate random blocks of memory anywhere you want to build something.
Right. Complete freedom. But there's a massive catch. The warehouse doesn't keep track of what you put in it. You get a pointer, basically a physical address to where your data is. If you accidentally overwrite or lose that pointer, the data is still sitting somewhere in the warehouse, but you can never, ever find it again.
That's a memory leak. And the explicit heap also suffers from memory fragmentation.
Right.
As you allocate and free different sized blocks over time, the warehouse becomes riddled with tiny, unusable gaps. Managing that chaos is entirely the programmer's burden in languages like C or C++E.
Which sounds terrifying, honestly. And it's exactly why languages like Python or Java use the fourth neighborhood, which is implicit heap dynamic variables.
Right. You still get all the flexibility of the massive warehouse, but the language's runtime environment manages the addresses behind the scenes. Like if you type names equals a list of Ann and Bob, the system implicitly carves out the heap space for you.
But there is no such thing as a free lunch in compiler design. If the system is managing the warehouse, it means you're paying the ultimate runtime tax.
Garbage collection.
It's exactly. The runtime environment literally has to halt your program's execution, sweep through the entire warehouse, find the boxes that don't have pointers attached to them anymore, and clear them out.
It's an enormous performance hit. You're basically trading raw execution speed for safety and convenience.
So we know where the data lives,
Yeah.
and we know how long it lives, which is its lifetime.
Yeah.
But who is actually allowed to look at it?
This raises an important question because we have to strictly separate scope from lifetime.
Right.
They are related concepts, but they operate on completely different axes. Scope is about visibility, which specific statements in your code are legally allowed to reference a variable.
Okay.
Lifetime is about existence, how long the data physically remains in memory.
And the distinction between the two becomes painfully obvious when you look at static scope.
Yeah.
Static scope is determined entirely at compile time based on the physical layout of your code. It's usually based on nested blocks.
Let's say you have an outer function that declares a variable and then it calls a nested inner function. If that inner function declares a new variable with the exact same name, the outer variable is suddenly hidden. It's temporarily out of scope. You cannot see it or access it by name from inside the inner function.
But its lifetime hasn't ended.
Exactly.
It's still sitting perfectly intact in the memory stack. It's just invisible for a minute.
Right, and the compiler has to carefully track this using a referencing environment. At any given moment, the referencing environment is the exact dictionary of variables that a specific line of code is legally allowed to see. In statically scoped languages, the compiler figures this out just by walking up the nested blocks of code.
But then you have dynamic scope, which just throws the physical layout of the code out the window.
Completely.
Dynamic scoping determines visibility based entirely on the calling sequence, like the chronological history of the call stack.
Yes. In dynamic scoping, if a function needs a variable, the runtime just looks at the function that called it. If it's not there, it looks at the function that called that function, tracing all the way back through the execution history.
That sounds like an absolute nightmare to debug.
Oh, it is.
You can't just look at a block of code and know what a variable refers to. You have to trace the exact, unpredictable paths the user took through the program just to get there.
It is notoriously difficult to maintain. A function's behavior can change wildly depending on who called it. That's why static scoping, often paired with object-oriented encapsulation, has essentially won the war in modern language design. Reliability just trumps extreme flexibility.
So what does this all mean for you, the listener? We've journeyed through von Neumann bottlenecks, floating point math and mechanics of the heap, and referencing environments. But let's bring all of this theoretical architecture back down to earth for your immediate survival in CS330.
Good idea.
Because you are heading into late March. Week 9 and 10 are here. Lab 7, the parser, is behind you, and Lab 8 is staring you right in the face.
And Lab 8 is AST decorating, abstract syntax tree decorating.
Right.
Everything we just discussed isn't just theory anymore. It is the exact blueprint for what you are about to build.
Exactly. When you decorate an AST, you are literally writing the tree traversal algorithms that physically enforce these rules.
Yeah.
You are building the referencing environments.
Yep.
As your code walks down the branches of the syntax tree, you are calculating the static scope to ensure that when a programmer asks for variable X, they're actually legally allowed to see it.
You are resolving those complex binding times. You are actively building the glass box. You are creating the magic trick for the next programmer who uses your compiler.
And a quick reminder on how you're allowed to build it. The course's LLM rules are in full effect. You need to complete at least 2 exercises in I've got this mode, purely your own brain, no AI assistance whatsoever.
But you also have the vibe coding mode for iterating on prompts, provided you use proper attribution, and the you do it mode where you act purely as the prompt engineer. Just keep an eye on your quota. You need at least 10 LLM exercises this semester.
And, hey, if writing the traversal logic for those referencing environments in Lab 8 starts to melt your brain, or you burn through your LLM tokens for the week, don't panic. You still have those 2 3-day extension coupons from the start of the semester.
Oh, right, the coupon.
Yeah, you can burn one to buy yourself time on the lab, or save them for a free point each on your final grade. Strategic choices.
Definitely a good safety net to keep in mind.
So as you dive into your AST traversal algorithms, I want to leave you with a final thought to mull over. We've spent this entire deep dive looking at how compilers manage rigid memory constraints and predictable binding times. But computing is rapidly approaching the quantum era.
Oh, wow. That changes the paradigm entirely.
Right. If dynamic typing is already pushing our classical runtimes to their absolute limits just by swapping strings and integers around, what happens when we introduce quantum superposition? How does a language designer even begin to write binding rules for a variable whose value is technically a 0 and a 1 at the exact same time until the moment it's evaluated? Who pays the runtime overhead for a variable that holds multiple states at once?
That is the ultimate referencing environment problem right there.
Exactly. Keep that in the back of your mind. Good luck with the AST decorating. You've got this. Keep diving deep.